Hello, this is Professor Roman. Let's continue our study of linear algebra. We are talking about inner product spaces. We've discussed the definition and the corresponding analog to the fundamental theorem of linear transformations. It's a little different, of course. It tells us that an inner product is completely determined by its action on basis vectors, and also that those values can be specified any way we want as long as the matrix of inner products, the so-called Graham matrix, is in fact positive, definite. Let's take a look at some of the properties of inner products and inner product spaces. The following result is very simple and yet quite useful. Let V be an inner product space. Two vectors u and v in V are equal if and only if they're inner products with all other vectors, with in fact all vectors are equal. So u equals v if and only if inner product uw equals inner product vw for all w in the vector space. The next result points out one of the main differences between real and complex inner product spaces, and also will be important later on. So let V be an inner product space and let tau be a linear operator on V. For both real and complex inner product spaces, if tau v w is 0, the inner product of tau v with w is 0 for all vectors v and w, then tau is the 0 operator. If V is a complex inner product space, we don't need to check all of tau v inner product w. If tau v inner product v is 0 for all vectors in the vector space, then tau is 0. This, however, does not hold in general for real inner product spaces. So this is somehow a fundamental difference between real and complex inner product spaces. This holds for all complex inner product spaces, but not for all real inner product spaces. As to the proof of part 1, that's quite simple. We just set w equal to tau of v, which tells us that tau of v inner product with itself is 0. That happens if and only if tau of v is 0. And since this is for all vectors in the vector space, tau must be the 0 operator. For part 2, we need to work a bit harder. If u and v are vectors and r is a scalar, then we will look at the inner product of tau of ru plus v with ru plus v. This is 0 by assumption. When we expand this expression using the linearity of tau and the sesquilinearity of the inner product, we get this, which can be simplified to this. Now, setting r equal 1 gives us this equation, tau uv plus tau vu is 0. And then setting r equal to I produces this, similar to this but with a negative sign. And so together these two equations imply that tau u v is 0 for all u and v, and then part 1 tells us that tau is 0. Of course, since we set r equal to I, we need the underlying field to be the complex field, which is why this works. As to what happens in a real inner product space, it's conceivable that the result could still be true, but this proof doesn't work. Some other proof would be necessary, but that won't happen. And as a simple example, think about rotation 90 degrees in the plane, R2. Every vector, if tau is rotation by 90 degrees, then tau v is orthogonal to v for all vectors. Tau v is 0 for all v. But certainly tau is not 0. The additional structure of an inner product allows us to define some concepts, some new concepts, such as the norm or length of a vector, the distance between two vectors, and the orthogonality of vectors. The ability to define the norm of vectors could send us in an entirely new direction, away from algebra and towards analysis, and in particular the study of convergence and continuity. And we'll get into that just a tiny bit. I'm not going to digress into those into analysis, but I want to show you the path that you could take if you wanted to. There is a hierarchy of mathematical structures. It starts, this particular hierarchy, with something called a topological space, which is a general setting in which one can define topological notions such as continuity, convergence, compactness, and other things. Topology is a wonderful area of mathematics well worth studying. Within the family of topological spaces, we find mathematical structures known as metric spaces, and those are mathematical structures that are non-empty sets that have a distance function defined on them. Not all topological spaces have a distance function. So a distance function is also called a metric. Metric spaces are topological spaces, but they're very special types. In metric spaces, there is a specific, by definition, there's a specific notion of distance, and that can be used to define convergence and other topological notions. A special type of metric space is called a normed space. A norm is a measure of length for vectors in a vector space. Inside an even smaller class of structures are the inner product spaces. So we have this hierarchy: topological spaces, special case metric spaces, special case normed vector spaces, special case inner product spaces. We pick up the algebraic structure with the normed vector space and the inner product space. Metric spaces are not required to have an algebraic structure, they're just required to have a distance function. And also, topological spaces are not required to have any algebraic structure. The study of topological spaces that do have algebraic structures belongs to a branch of mathematics known as algebraic topology. Let's take a closer look at some of these ideas. Then a norm, if V is an inner product space, the norm or length of V is defined to be the square root of V inner product with itself. A vector V is a unit vector if its norm or length is equal to 1. Here are the basic properties of the norm on an inner product space. The norm of every vector is greater than or equal to 0, and it's equal to 0 if and only if the vector is 0. The only vector that has norm 0 is the 0 vector, as you would expect. The norm, if R is a scalar and V is a vector, then the norm of RV is the absolute value of R times the norm of V. This is easy to remember. You can pull the R out, but you have to take absolute values because the norm of every vector is non-negative. There's a very famous inequality called the Cauchy-Schwarz inequality, which states that the absolute value or norm of U inner product with V is less than or equal to the product of the norms of U and V. This norm with the single bar is the norm of a scalar. So for real numbers, it's the absolute value. For complex numbers, it's usually called the norm. And equality holds in the Cauchy-Schwarz inequality if and only if one of U or V is a scalar multiple of the other. So they point in the same direction or in opposite directions. But also this would hold if either U or V was 0. We also have the triangle inequality. The norm of U plus V is less than or equal to the norm of U plus the norm of V. And in the real case, equality holds for two non-zero vectors U and V, if and only if V is a scalar multiple, positive scalar multiple of U. This inequality doesn't have a name as far as I know. It's simply useful. Here's another inequality, also useful. Finally, we have the parallelogram law. Two vectors U and V. The norm of U plus V squared plus the norm of U minus V squared equals twice norm U squared plus twice norm V squared. I suggest that you draw a picture in R2, pick a couple of vectors U and V, draw these pictures, and you will see why it's called the parallelogram law. I'm only going to prove for you the Cauchy-Schwarz inequality and the triangle inequality. I'll leave the rest for you as practice. For Cauchy-Schwarz, if either one of the vectors is 0, let me write this up again. If either one of these vectors is 0, then both sides are 0. And so we actually have equality. So we can assume they're non-zero vectors. If r is a scalar, then we can take a look at u minus rv norm squared. That's bigger than or equal to 0. It's equal to this, which expands to this. What to do? Well, if we choose r carefully, we can simplify this quite a bit. If r bar is taken to be vu divided by vv, then this value here becomes 0, and so we're left with 0 less than or equal to u minus r bar, minus r bar uv. So here's the uv and here's the r bar. And this is the norm of u squared minus the absolute value of uv squared divided by the norm of v squared. That is the Cauchy-Schwarz inequality. Just scramble things around. When does equality hold in this? It holds if and only if equality holds right here. In other words, if this quantity is 0. And this will be 0 if and only if u is equal to rv. As to the triangle inequality, well, this just is a brute force kind of proof. Norm of u plus v squared is the inner product of u plus v with itself. We expand. Now notice that these two terms in the center, uv plus vu, are complex conjugates of each other. And when we add a complex number to its complex conjugate, we get twice the real part of the complex number. And that is less than or equal to, I've just copied this, but the real part of a complex number is less than or equal to its norm, the norm of the complex number. So we can write this, and now we can use the Cauchy-Schwarz inequality. This is the norm of u inner product v less than or equal to the product of the two norms. And this can be written this way. And so looking at the first item and the last item, since everything underneath the square is non-negative, we can drop the square and we get the triangle inequality. As an example, for the inner product space Fn, so this is either Rn or Cn, the Cauchy-Schwarz inequality looks like this, the triangle inequality looks like this. Rather ghastly looking formulas that are much more trouble to prove directly, but these are special cases of the theorem we just discussed. One of the most interesting observations to make about inner products is that an inner product can be recovered from the norm. So if someone says, I have an inner product space, and I will tell you the norm of every vector, the length of every vector, you can figure out what the inner product is. That's a bit surprising, because it sounds like the inner product, being a function of two variables, two vectors, might have more information in it than just the length of each vector, but in fact it does not. So that's something to think about. The reason this statement is true is that it follows from what are called the polarization identities, and the proof of these is just, again, a brute force computation, so I'm leaving it for you. If V is a real inner product space, then the inner product of U and V is 1/4 the quantity U plus V norm squared minus U minus V norm squared. So if we know the norms of every vector, we know the inner product of every pair of vectors. The complex version is more complex, but the idea is the same, and the proof is analogous, just a matter of writing out the right-hand side here and simplifying. Okay. Now, let's again talk about this picture here, this hierarchy, just briefly. And again, we're not going to go into this in any detail in this course, because it really belongs to mathematical analysis more so than algebra. A normed vector space, real or complex, also just called a normed space, is a vector space together with a norm function. And the norm function has to satisfy three properties. The norm of every vector has to be non-negative, with equality here if and only if V is the zero vector. We have to have this type of homogeneity. You pull out the scalar, take the absolute value, and the triangle inequality must hold. So, normed spaces are a generalization of inner product spaces, because every inner product space is a normed space. We just proved that. But there are normed spaces that are not inner product spaces. If you have a normed space, you might say, well, why not use these polarization identities, like this one complex case, to define an inner product? Well, what you can do is you can define a function of two variables this way, but it won't necessarily satisfy the properties of an inner product. It won't necessarily be positive definite, sesquilinear, and conjugate symmetric. This will happen, in other words, the norm from a normed space will define an inner product, and so the normed space is an inner product if and only if the norm satisfies the parallelogram law. So let me go back to that. I can find it here. Here we go. This is the parallelogram law, strictly in terms of norms. The norm of u plus v squared plus the norm of u minus v squared is twice norm of u squared plus twice norm of v squared. So if you are presented with a normed space, and you would like to know if it's an inner product space, if the norm defines an inner product via the polarization identities. You can answer that question very simply in theory. Does the norm satisfy the parallelogram law? You know, if the norm does not satisfy the parallelogram law, then it doesn't define an inner product, because the inner products, the norms that come from inner products, do satisfy the parallelogram law. The surprising thing is that it works the other way. The parallelogram law is both necessary and sufficient to conclude that the norm actually defines an inner product, that the norm is the norm of an inner product. And I left proof of this very interesting result as an exercise in the book, and I think I gave some hints. In a normed space in general, we can define convergence. So this applies then also to inner product spaces. A sequence of vectors v sub n converges to a vector v if the limit of vn minus v norm is 0. So the norms of vn minus v must tend to 0. In other words, in loose terms, the vectors vn approach the vector v. As you may know if you studied analysis, a sequence of vectors is called a Cauchy sequence if, speaking informally, the terms of the sequence get closer together as we go farther out in the sequence. If you studied mathematical analysis, you would have studied this concept for real numbers, for the real line, and possibly a more general context. The formal definition is that for every positive epsilon, there's a positive integer m such that the difference, the norm of the differences, vi minus vj, is less than epsilon for all I and j bigger than m, bigger than or equal to m. When a normed space has the property that every Cauchy sequence actually converges to some element of n, we say that the normed space is complete. Just because vectors get closer and closer as we move out in a sequence doesn't mean that those vectors approach a specific vector. For example, the real numbers form a complete normed space where the norm is the absolute value. But the rational numbers do not. They form a normed space, but it's not complete. All you have to, I should have made that a little clearer here. All you have to do is take a non-rational real number like the square root of 2, form its non-repeating decimal expansion, and just take additional terms, partial expansions, if you will. 1, in this case, 1 for a square root of 2, 1, 1.4, 1.41, 1.414, 1.4142. These are all rational numbers. They're terminating decimals, and they get closer and closer to each other as you go farther out. So this is a Cauchy sequence of rational numbers, but it does not converge anywhere. It does not converge within Q, the rational numbers. it happens to converge to an entity which is not rational, the square root of 2. A complete normed space is called a Banach space, and Banach spaces have a very rich theory. Whole courses, whole books, mathematicians can specialize in Banach space theory, and they form, the theory of Banach spaces forms a very important branch. It's a sub-branch of an important branch of mathematics called functional analysis. A complete inner product space is called a Hilbert space. Hilbert spaces are pretty much a direct generalization of Euclidean and unitary space. They also have a very rich structure and many applications to physics. For example, quantum mechanics relies very heavily on the theory of Hilbert spaces and operators on linear operators on Hilbert spaces. Functional analysis in large part is composed of the theory of Banach spaces and the theory of Hilbert spaces. Now let's take a look at the distance function. The norm in an inner product space can be used to define the distance between two vectors. And here's the definition. The distance d of uv between the two vectors u and v is simply the norm of the difference between the two vectors. And these are the properties of the distance function in an inner product space. The distance between any two vectors is non-negative, and it's equal to 0 if and only if the two vectors are equal. The distance function is symmetric. The distance between u and v is the same as the distance between v and u. And the triangle inequality holds. Any non-empty set, doesn't have to be a vector space, that has a function d from v cross v to r that satisfies these three properties is called a metric space. And the distance function is called a metric. So any inner product space, in fact any normed space, is a metric space. And so that's the origin of this picture. Any inner product space is a normed vector space, and any normed vector space is a metric space. And all of these fall under the purview, under the umbrella of topological spaces. I'm not going to define a topological space for you. That would take us way outside the scope of this course. But you can certainly Google that. The definition is not that complicated. Now let's take a look at orthogonality. This concept can be defined because of the presence of the inner product. You can't define orthogonality in an arbitrary normed space or metric space. Two vectors in an inner product space are orthogonal, written this way. This is the symbol for perpendicular if their inner product is 0. Some people might call these vectors perpendicular. I think that word is better used in the context of geometry, plane geometry. So I'm going to stick with the more formal word orthogonal. That's more common and more appropriate, I think. We can extend this idea to subsets of an inner product space are orthogonal if every vector in X is orthogonal to every vector in Y. A subset O of the inner product space V is an orthogonal set if O is pairwise orthogonal, meaning that when you take any two distinct vectors in O, they are orthogonal. If in addition O is a basis for V, we would call this orthogonal set an orthogonal basis. And these will play a key role in our upcoming discussions. An orthogonal set of unit vectors, if every vector in O has unit norm, then we call it an orthonormal set. And an orthonormal set that's also a basis is called an orthonormal basis. So we're combining two different concepts here. Orthonormality, which in itself is two concepts, orthogonality and normality, every vector is unit length, and basis, orthonormal basis. Of course, given any non-zero vector V, we can always get a unit vector by dividing, I shouldn't say that, by multiplying V by the reciprocal of its norm. That's why we have to have a non-zero vector, because you can't stick 0 in the denominator here. This process is called normalizing the vector V, and it's something we'll do frequently. So it's a simple matter, at least in theory, to construct an orthonormal set from an orthogonal set of non-zero vectors. Orthogonality is a very strong property. It's much stronger than linear independence, for example, because every orthogonal set of non-zero vectors is linearly independent. But the converse is certainly not true. You can have linearly independent subsets of R2, for example, that are not orthogonal. And the proof here is quite short. Any orthogonal set of non-zero vectors in, I really should say, an inner product space is linearly independent. Here is the test for independence. We write a linear combination equal to 0. We have to show all the coefficients are 0. But for this, all we have to do is take the inner product of this linear combination with a specific vector u sub k from the orthogonal set. When you expand this, ui uk is 0 unless I equals k, because this is an orthogonal set. So only one term survives the expansion. And since uk, inner product uk, is positive, because uk is non-zero, all the coefficients must be 0. So O is linearly independent. Orthogonal sets of non-zero vectors are linearly independent. That makes a lot of sense when you think about R2 and R3. They're pointing in perpendicular directions. It sounds a lot like they're linearly independent. For example, here is the vector space of continuous functions on the interval 0 to 2 pi. this is an inner product. 1 over 2 pi, integral from 0 to 2 pi, f of x, g of x, bar, complex conjugate. If we take the exponential functions, fn of x equals e to the inx, for n bigger than or equal to 0, then if we take two of these, take their inner product, m and n are different, get this integral, which is this integral, evaluates this way, get 0. So this set of functions is orthogonal. As to the norm of each function, norm of fn squared, which is easier to compute than the norm of fn directly, fn inner product itself, this integral equals 1. So the functions in fn form actually an orthonormal set. And this is why it is customary to put this constant 1 over 2 pi in front of the integral. Without this constant, it's still an inner product, but these functions are not unit length. Okay. This is a common technique, you might say, and we'll see it again soon. Now we come to a critically important point, and that is the great advantage of orthogonal sets. An orthonormal sets amounts to the same thing as long as the vectors are non-zero. An orthonormal set of vectors has a very important practical advantage and therefore theoretical advantage over arbitrary linearly independent sets. In particular, any vector in the span of the set, and so if O is a basis, that means any vector in the whole vector space, has a very simple representation as a linear combination of the vectors in O. Since O is linearly independent, we know, of course, that any vector in the span is an essentially unique linear combination of the vectors from O. Now, normally, if we didn't know anything more about the U's except they were independent, to find the coefficients would require solving a system of equations. But because we have an orthogonal set, or an orthonormal set, orthonormal set in this case, the coefficients R sub I can be computed in a very simple way. We just take our vector v, take the inner product with u sub I, it's this expansion, inner product with u sub I, and as we've seen already, all the terms go away except one. And since since the ui's have norm 1, this is just ri. If they didn't have norm 1, you'd have to keep this inner product, which isn't a big deal. So this works for both orthogonal and orthonormal sets. But the orthonormal sets, it's a little simpler. So the coefficient R sub I of u sub I is just the inner product of u sub I with v. In this order, v inner product ui. I think I might change that. So let O be an orthonormal set of vectors in an inner product space, then any vector v in the span of O is an essentially unique linear combination that looks like this. V is V inner product U1, U1 plus V inner product U2 times U2 and so on. And here I mentioned that if O is simply an orthogonal set of non-zero vectors, then we can normalize each of the vectors. And the expression then looks like this. So, to recap, when you have an orthonormal set of vectors, an orthogonal set of non-zero vectors, or in particular an orthonormal set vectors, it's very easy to represent every vector in the span of that set as a linear combination. The coefficients are very easy to compute. They're just the inner product of the vector with each of the vectors from the orthonormal set. Here's another useful advantage of orthonormal bases in this case. Let V be an inner product space and let O be an ordered orthonormal basis for V. The Graham matrix is the identity matrix because the U's are orthonormal. And so that beautiful formula we derived a while ago, connecting the inner product of two vectors U and V in the inner product space with the standard inner product of their coordinate matrices, looks like this. And it tells us in words that the inner product of two vectors is equal to the standard inner product of their coordinate vectors. Nothing could be simpler, but it requires an orthonormal basis for this to work. Otherwise, the Graham matrix will not be the identity matrix, and you'd have to stick it back in here. The well-known Pythagorean theorem holds in arbitrary inner product spaces, but there is a wrinkle with respect to the base field. If V is an inner product space for all vectors U and V, if they are orthogonal, then the norm squared of the sum is the sum of the norm squared. This is the Pythagorean theorem. C squared equals A squared plus B squared. In the real case, it goes both ways. If you have two vectors that satisfy this Pythagorean formula, they are orthogonal. In the complex case, it only goes in one direction. For the proof of this statement here, this implication, if the inner product of U and V is 0, then when we expand the squared norm of U plus V, we just get what we want. And I'm leaving it for you to show that for a real vector space, if this Pythagorean theorem holds, then the inner product of U and V must be 0. Because of the presence of the inner product, we can define orthogonal direct sums. They're simply direct sums in which every pair of sum ends is orthogonal. So here's the definition. V is an inner product space if we have at least two subspaces. We will write this S1, I don't know how to read this a dot with a circle around it, up through Sn. This denotes the fact that the direct sum exists. And you remember that that means that, or it's equivalent to saying that the subspaces S1 through Sn are strongly, essentially disjoint. And so the sum, which always exists, is actually a direct sum. And that the summands are pairwise orthogonal. So Si orthogonal to Sj for I different from j. This sum is called an orthogonal direct sum. It's a direct sum whose summands are orthogonal. When we just have two summands, when v equals s, I don't know, dot circle t, we say that s and t are orthogonal direct complements of one another. Now we come to a point that's going to require careful attention. I've just defined orthogonal direct complement. And it looks like this. S and T are direct complements of each other. We usually just say complements of each other. But they're also orthogonal, which makes them orthogonal direct complements. There is something called the orthogonal complement, and it's different from the orthogonal direct complement, but related. So that's what we have to talk about now. Any subset X of an inner product space has what we call an orthogonal complement. It simply means the set of all vectors that are orthogonal to everything in X. It's a very simple definition. V is an inner product space, the orthogonal complement of a subset X of V. And this is read X perp, P-E-R-P. Here, this comes from the word perpendicular. X perp is the set of all vectors in V that are orthogonal to everything in X. Brief theorem that I leave for you to prove. The orthogonal complement of any subset is in fact a subspace, and that's very nice. If S is a subspace of V, then S and its orthogonal complement, S perp, are essentially disjoint. And so the orthogonal direct sum exists. To say that these are essentially disjoint means to say there is no non-zero vector that belongs to S and is also orthogonal to everything in S. And I don't want to give away any more of the proof. Now, it's important to observe that this theorem does not say that S orthogonal direct sum, S perp, is all of V. It just says that this exists as a subspace of V then. In other words, that the sum is direct and that the two summands are orthogonal. That's all it says. So, this does not imply that the orthogonal complement, S perp of S, is an orthogonal direct complement of S in V. It doesn't imply this, because we don't necessarily have this sum equal to V. We do know, of course, we've known for some time, that every subspace S of V has a direct complement, a subspace for which this happens. So the question arises, does every subspace S have an orthogonal direct complement? Well, if S does have an orthogonal direct complement, call it T, then of course T must be orthogonal to S, and in fact T has to be the orthogonal complement S perp of S. Why? Well, if V is the orthogonal direct sum of S and T, then T is orthogonal to S. It just may not. So it's contained in S perp. That's part of the definition of orthogonal direct sum. These two are orthogonal, so T is contained in the orthogonal complement of S, and vice versa. S is contained in the orthogonal complement of T. So now we have V equals S orthogonal direct sum T contained in S orthogonal direct sum S perp, which of course is contained in V, so we have equality. So we have this. And from this, one can show that S perp is contained in T. And I'm going to let you work on that. And so, therefore, the two are equal. So let's go over this and be sure it's clear. We're trying to decide whether every subspace S of V has an orthogonal direct complement. It has an orthogonal complement, it's just everything orthogonal to S. But does it have is there a subspace T for which this holds? What we have just shown is that if there is such a T, it's got to be S perp. It's certainly got to be contained in S perp, but if it's properly contained in S perp, this sum is not going to be all of V. If a subspace S of an inner product space V has an orthogonal direct complement, then it must be the orthogonal complement S perp of S. So if V equals S orthogonal direct sum T, then T is in fact S perp. But we still haven't answered the question. It doesn't tell us if the orthogonal complement S perp of S is always an orthogonal direct complement. It tells us that if we know somehow ahead of time that there is an orthogonal direct complement, it's got to be S perp. But if we don't know that there is an orthogonal direct complement, we can't apply this theorem, and we have nothing. So we still don't know if this always holds. Well, I should say unfortunately, it just happens to be the case that it does not always hold. As a matter of fact, it's possible in some inner product spaces it happens that S is a non-zero, non-trivial, proper subspace of V, but S perp is trivial. And here's an example. Little L2. This is the inner product space of all square summable infinite sequences. So this is the requirement. This is the inner product. Consider the subspace of L2 that consists of the sequences with finite support. They are square summable because this sum reduces to a finite sum. All but a finite number of terms are 0. So it's certainly finite. And consider these standard basis vectors we've discussed before. There's a single 1 and all zeros. Which vectors in L2 are orthogonal to this subspace? Well, the thing is, when you take any sequence in S-perp, you take the inner product, in fact any sequence X with EI, you just get the ith component of the sequence. So if X is in S-perp, it's orthogonal to all of the E sub i's, which means all of its components are 0, which means it is 0. So S-perp is trivial, and so S orthogonal direct sum S-perp is just S itself. Okay. And S is a proper subspace of L2. So it is not the case that this always holds. What we can say is if S has an orthogonal direct complement, this must be that orthogonal direct complement, and this will hold. But if we don't know that there is an orthogonal direct complement to S, we can't say this. Nevertheless, we will see very soon that if the subspace S is finite dimensional, even if the whole space is not, then this will hold. Or in words, the orthogonal complement of any finite dimensional subspace is an orthogonal direct complement. See, that doesn't happen here because this subspace of sequences with finite support is infinite dimensional.